Hello everyone, this is Charlie Su. I'm CTO and EVP of Andis Technology. I also serve as Vice Chair of Risc-V Technical Steering Committee. Today I would like to talk about Andis' involvement in Risc-V, open source, and academia. This is the agenda of my talk. First, I will give an overview of Andis, and I will talk about Andis Risc-V processor called V5 from two perspectives, for control path processing and for data path processing. Then I will talk about Andis' involvement in the public, and I will give a short conclusion. Andis is a 15-year-old pure-play CPU IP vendor. We are a public company since 3 years ago. Our headquarters is in Taiwan, Hsinchu, with office worldwide. Andis is a Risc-V founding and premium member. In addition to a major open source contributor and maintainer, Andis plays an active role in Risc-V International, including Risc-V Ambassador, Task Group Chair's Co-Chair, TSC Vice Chair, and Director of the Board. Andis has over 100 years CPU experience in the Silicon Valley, and 80% of our employees are R&D engineers. We have over 200 licensees, and our professional Andis IDE has over 17,000 installations. And total shipment of Andis embedded SoC by our customer has surpassed 5 billion since last year. And the annual run rate has over 1 billion since 2018. So how did Andis run into Risc-V? We know Risc-1 to Risc-4 were developed in the 1980s. And then Andis was founded in 2005. So our architecture, Andis has 3 generations, V1, V2, V3. We develop our own tool chain, so GCC and Linux are upstream. We develop many cores, and our customer ship product from MCU to gauges, storage, to data center with high volume. Then we worked, and then we found Risc-V started showing up in 2014, and Risc-V International was formed in 2015. So we did some detailed analysis. From the ISA perspective, we found that Risc-V was very similar to Andis V1 to V3 more than other popular ISA, such as ARM, MIPS, PowerPC, and Spark. We have the same 32 and 16-bit instruction, and the register can be 16 and 32. And we both doesn't have delay branch, no predicate execution, no condition code, and PC cannot use as a general purpose register. The only difference is that Risc-V hardwire R0 is 0, but Andis does not. But this is a relatively minor difference. So we decided to join Risc-V Foundation and use Risc-V as our basis for Andis V5. And the rest are history. Andis Risc-V processor is called V5. We started with 25 series, which are 5-stage pipeline, 1.1 gigahertz, worst case at 28 nanometer. 25 series support both RV32 and RV64. Its N and D prefix core are fast and compact cores with floating point and DSP, and prefix A cores are Linux capable, and suffix MP cores has cache coherency support with up to 4 cores. And 27 series are also 5-stage pipeline, 1.1 gigahertz. In addition to the feature, 25 series has 27S main boost, which improve memory subsystem performance, and also Risc-V vector extension. In particular, NX27V is the first commercial Risc-V vector processor. And 45 series are superscalar, dual issue, 8-stage pipeline, 1.2 gigahertz. So those cores have some common feature, including Risc-V baseline instruction and AC, and caches local memory, ECC, branch prediction, and also a series of NDIS extended features, including Ctocand, power break, stack safe, and NDIS custom extension. We're going to spend some time to talk about them a little bit later. And in the bottom left corner, we have tiny N22, which is a two-stage pipeline, 700 megahertz. V5 processors are used in diversified applications. They can be found in IoT edge devices, running Bluetooth, Wi-Fi, or Zigbee. They can also be found in personal devices such as smartphone, multimedia devices, true wireless earbud, consumer storage, and on the way to cloud, they can also be found on devices such as 5G, macro cell and small cell, enterprise storage, and data center AI accelerators. Our customer using V5 processor in advanced technologies from 14 nanometer to 7 nanometer. And one of our innovative customers using over 1,000 instances of V5 processors. Next, let's look at V5 support for control paths. Control paths call for good integer performance. The single issue 25 and 27 series has an industry-leading Core-Mark, DMIPS, and M-Bench IoT in both RV32 and RV64. And the dual issue 45 series add about 50% performance on top of its counterpart of single issue on both RV32 and RV64. Control paths also benefit from some application support as follows, such as hardware handling of misaligned access to ease supporting of software from x86 and ARM. Both architecture natively support misaligned access in hardware. Stack safe is hardware-supported stack protection to detect stack overflow and underflow. And in power break, software can set CSR to control or enable periodic pipeline store to save power. And Man-Boost is a combination of instruction and data prefetch, multiple outstanding transaction, and dynamic write policy. Man-Boost is first introduced in 27 series, which achieve 3x bandwidth and 50 to 70% latency compared to 25 series. Control paths often need real-time response and OS support. For this, first we have vectored PRIC IP to support V5 processor. Its enhancement over the standard Risc-V PRIC is in priority-based preemption with vector dispatch to interrupt service routine. It's greatly reduced interrupt latency. It's easy to program. Software only need to initialize priority once and never need to deal with it again. Its configuration is flexible. It supports up to 1023 interrupt sources, 255 priorities, and up to 16 targets. V5 also supports Risc-V standard MMU in virtual address bits, that's SV 32, 39, and 48. And all the page sizes from kilo, mega, giga to tera pages. In the microarchitecture level, V5 also supports fully associative 4-entry or 8-entry micro TLB for instruction and data, and 4-way 32 to 128 entry shared TLB. In addition to PMP, physical memory protection, V5 also supports programmable PMA, physical memory attribute. The attribute can be cached, uncached, or device region. For cached region, the write attribute can be write back or write through. Next, let's look at V5 support for data paths. First, we have RVP extension or PEG SIMD DSP. It's an efficient and low-power SIMD DSP ISR based on integer register file. An example of SIMD instruction can perform 4A by A multiplication and add the results into a 32-bit value RV32P performed one set of such operation, while RV64P performed two independent sets of such operations. RVP is very suitable for processing audio, voice, small image, and slow video. It has been supported by IAR embedded workbench since v1.3. Let's use the following speedup table to show the benefit of RVP. Here, the speedup is measured over the performance with DSP instruction and without DSP instruction on the same core. So we implemented CMSIS compatible DSP library with over 200 functions. For RV32P, its average is 1.8x speedup, while the maximum is 5.2x speedup. For RV64P, the DSP library average is 2.5x speedup, while the maximum is 11x. On the application part, we have MP3 decoder, person detection, AMR voice codec, and keyword spotting. They can go from 2x speedup to over 8x for RV32P, while for RV64P, using image clarification Ctocand can get to 14x speedup, and object detection using PNet and almost 9x speedup. So this is very impressive. But how do we compare with other ISA? Next, let's look at RVV, or vector extension, and NDIS vector processor, NX27V. 27V implements the latest RVV spec, and it supports various data formats, including the standard int8 to int64 and FP16 to FP64, and also NDIS extended format, bflow16 and int4. 27V has a simple and efficient scalar unit, which is 5-stage pipeline. It can execute instruction to retire efficiently. And for RVV instruction, though they would be fed into a vector processing unit or VPU, their actual execution starts after they are retired. And there are multiple functional units operating parallel. They are executed out of order with scoreboard to keep them in order when necessary. RVV instructions are trainable and mostly are fully pipelined. VPU supports a VLAN and SIMD with configuration ranging from 128 bits to 512 bits. And there are two independent memory access paths. One is from RVV load store instruction through Dcache and system bus, and another is ACE load store instruction. This is NDIS custom extension through streaming ports, and both are load data into the vector register. Next, let's look at RVV tools and performance. RVV are supported by the standard tools in NDIS IDE, including NDSIM, near cycle accurate simulator, compiler with RVV intrinsic function, assembler, debugger, and ICE. And we are also implementing computation library optimized for RVV. And there are also advanced tools, including LLVM IR support for AI compiler, NDSysC, which is basically NDSIM in System C, and also NDIS Clarity, which is pipeline visualizer and analyzer, help you to optimize your inner loop. And here are a list of functions to show the benefit of RVV. And so F32 basic math function can get about 19x speedup on NX27V. And RGB depth-wise, point-wise CNN are sophisticated functions used in MobileNet. They get on average about 20x speedup. And the root CNN is relatively simple, and you can get almost 70x speedup. Then we have filter function. F32 get about 19x speedup, and Q7 get 39x speedup. And last, we have S32 single precision metric multiplication with dimension 32 by 32 by 32, and it get very impressive 57x speed up on NX27V. So the data is measured on 27V FPGA and compared with a scalar code, which compiled with a high optimization. And the configuration of 27V is 512 bits SIMD and 512 bits VLAN. And this custom extension, ACE, which is a powerful framework to design custom instruction. All V5 processor supports ACE. There are two paths to accelerate data-intensive computation: data I/O and compute acceleration. For data I/O, it is usually done by DMA with double buffer, so compute hardware working on one buffer while DMA engine working on the other. So when both are done in one phase, and software switch a buffer and continue on the new phase. So ACE is really focused on compute acceleration. There are two common ways to use ACE. First is to design ACE instruction to perform computation directly, such as metric computation, bit manipulation, crypto function, and header parsing. Another is to design ACE instruction to control existing hardware engine. So instead of going through long latency of the bus, suffer bus contention, and also limited width, ACE allow user to design instruction to send, say, 200 bits command every cycle to hardware engine. So this is a very efficient way to keep hardware engine busy. So ACE is supported by Copilot tool, which can automatically generate ACE in design, including RTL, simulator, and all the required toolchain. Next, let's look at Andy's involvement in Risc-V, open source, and academia. Andy's and Risc-V. Let's look at Andy's activity in Risc-V task group. P extension is a PEC SIMD DSP. It has over 300 instructions in the proposed draft. They actually come from Andy's, where we design over 150 SIMD DSP instructions in our previous Andy Star V5 ISA, and we implemented in several core, and they are one of the most popular product we had in the past. So we contribute its enhanced version to 300 instruction SP extension draft and run task group, and right now we are kind of converging with the feedback from the community. And next is a fast interrupt extension. Risc-V PRIC, or platform level interrupt controller, is very suitable for Linux type of application, but for embedded real-time system, it's not very efficient. So and is based on our past experience, extended PRIC with vector interrupt, and so also priority-based preemption. And then after we presented, we formed a task group with Sci-Fi, so to enhance the spec and to promote for the whole community. And next is Risc-V DV, which was a Google DV before. It is a random instruction generator for processor verification. While we are working on the our vector processor, we start finding its usefulness, and we added vector extension to Risc-V DV and contributed our port to upstream. And then afterward, Google helped to move it to new framework so that you continue to enjoy the good framework. And last but not least, Risc-V ambassador. Our colleague Flo get elected as an Risc-V ambassador. It's not because of his charming smile, but because he's very patient to promote Risc-V technology and to the community, and also engage with members and to facilitate the whole community growth. Andy is also very active in Risc-V open source. In the GNU-based toolchain, Andy introduced GCC test suite, and we bring its importance to the GNU toolchain, and using it to run through a GC test and find out several issues at early stage and help to provide the fix. And also RV32E compiler, which is to use just 16 register, and that's very important to enable the code-sensitive SOC. And in the LLVM-based toolchain, Andis published the first full Risc-V LLVM source code, including floating point and optimization support. This somehow encouraged the maintainer, Alex from Low Risk, to continue to work on LLVM to the status we have today. And LLD is a linker for LLVM, which is faster and smaller than Binutile LD. And this provides the port and serve as a maintainer and open source it. And in Linux stack, Andis also bring the LTP Linux test project concept to the community. It is just like GC test suite to GNU toolchain. It's very important to help to ensure the maturity, stability of Linux kernel. And Andis also ported several key utility for Linux, including perf, which is profiling tool, app trace for system call trace, Kazan for memory leak detection, and power management utility. And we also provide our hardware platform with Linux kernel to Fedora and OpenSUSE for their distribution development. So far, Risc-V community has Linux for RV64, but it lack of RV32. And for those who need it, Andis already ported and also provide the source code. And for U-boot, it's also very important part of the whole stack. Andis are the maintainer. We provide the initial port, help to merge the board support for other company. So last, Andis and academia. Andis has a university program. So far, we have over 70 universities in this program from Taiwan, China, US, Japan, Europe, and so on, including Sri Lanka. Sci-Fi last year has a world tour with seminar worldwide, everywhere, but they forget Sri Lanka. So far, 30 of them converted to Risc-V. The rest would continue be doing so. Some of them, it will take some time because the professor, they prepare the class material, lab, and so on. So they have initiative to kind of do that. Next, Andis also sponsor research program from university in the subject of compiler, architecture, and SOC. So what Andis offer is as follows. First is Andis Sci IDE, which include compiler, debugger, IDE, and near cycle accurate simulator. So with this, professor can create a lot of lab material for students to kind of exercise it and do embedded development. We also provide Andis Arduino compatible board, which is also an enhancement over the near cycle accurate simulator, especially for the embedded system class who like to have extension board and writing software to control that. For some hardware SOC related professor, they like to put their idea into the test chip. So Andis also provide our processor IP to them. So far we have we have 6 tape outs. Here are 2 examples. One is ultra low power keyword spotting processor using our processor IP, and the other one is CNN with optimized memory access. In addition, Andis has a so-called Andis Certified Engineer Test, which provide a certification process especially for students who are not CS or EE major, but they are very interested in embedded system, processor, and so on. So get a certification, also adding something to their resume. Conclusion. So Risc-V provides a great opportunity for open source community, and also it's a great vehicle for research because it provides a lot of new room for innovation, and also there's a lot of opportunity to influence the fast advancing architecture because it's kind of open. It's everyone's as long as you want to join. But as an ISA is as successful as its ecosystem, especially its software. So I'm hoping that more effort will put into software or ecosystem part of the research. So here are some examples of what I think is very important to bridging the Risc-V software and ecosystem gap. First, for example, we have the P extension, we have V extension, the instruction compiler library definitely will be there, but there's a lot of AI framework to supporting neural net library or OpenCV, OpenVX, LIMPAC, LAPAC, and so on. And that's some of them for high performance computing. So those need to come. And also, we talk about high performance computing and the parallel programming environment like OpenMP or OpenCL is also very important. And then there's a Java virtual machine, virtualization, and hypervisor, and so on. So with this, I conclude my talk. Thank you.